Madam, is my voice audible?
Yes, ma'am.
Okay. Madam, I have made you the co-host, and
Okay.
I am waiting for 2-3 more minutes. A lot of
Yeah, yeah.
students are joining in. Then we will start.
Sure. Sure, sure, sure.
Okay. Okay. I think a lot of. Okay. Okay. So, good afternoon and a very warm welcome to everyone. Our Honorable Director, Sir, Dr. Shudipta Chakraborty, Sir, our respected Principal, Sir, Dr. Ranjit Roy, and at the head of the department, Bapa Dipta Jana, Sir, and all my dear students. Thank you so much for joining us for today's webinar. My name is Bias Bhadro and I am the host for today's webinar organized by Department of Computer Science and Engineering, Chaibasha Engineering College. Today we are presenting TechIp 3 sponsored special classes on compiler design and it will be presented by Dr. Shuchishmita Chinara, eminent professor from National Institute of Technology, Rourkela. In the meantime, if you have any questions during the presentation, you may type them in the chat box in your Zoom control panel. I'll bring them up during the presentation and we will also have some time for questions at the end. You can also raise your hand using the Zoom control panel so that madam can directly address to your queries. So now without further ado, we will turn the time over to our presenter today. Dr. Shuchishmita Chinara Madam is associated with Computer Science and Engineering Department of NIT Rourkela. She has authored and co-authored multiple peer-reviewed scientific papers and presented works at many national and international conferences. Her contributions have acclaimed recognition from honorable subject experts around the world. She is actively associated with different societies and academics. Her academic career is decorated with several reputed awards and fundings. So now I would like to hand over the session to Dr. Shutishmita Chinara Madam. Madam, over to you.
Thank you so much, madam, for this nice introduction. So I can start with the presentation, right?
Yes, madam. Everyone can hear.
Okay. Thank you. So students, I think you can see my slides, right? Is this visible, ma'am?
Yes, sir, this is visible. One or two students can say whether it is visible or not. Madam is asking so that she may proceed.
It's visual.
It is visible, ma'am.
Okay. Thank you.
Visual,
Thank you.
ma'am.
Okay. Thank you. Thank you. So before I start the class, just students, few things I'd like to tell you so that the class can be interactive and you'll enjoy the lecture. First thing is that if you have any query at any point of time, just press the hand raising so that I can ask the question. I can clarify your questions, or you can give in the chat box so that, as madam said, I can take any of the
Sorry to
questions.
interrupt. The screen sharing part is okay, but the voice is breaking.
Voice is breaking. Is that for everyone, ma'am? Even for you also, is my voice breaking?
No. I think it is a problem at that particular student's end. Maybe it generally
Okay.
becomes clear after 2 to 3 minutes because on my side I can hear you clearly and see you properly also.
Okay. 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 So can you please check your, otherwise you can reconnect. Probably this problem may go. That would be the case. And so now I can start the presentation for the compiler design. And today is the first lecture. So in this lecture one, I like to suggest the book for this compiler design is, it's a very good book, standard book by Aho and Ullman. It's a compilers, its principles, techniques, and tools. Maybe you can go for the second edition. There are also the recent editions, you can go for that. This is a very standard book and I have referred most of the contents from that book. This is referred for all the undergrad students all over the country. So you can follow this book for the content and all. So to start with, the compiler design. What is a compiler? We talk always about a compiler. Which kind of compiler you are using? What is a compiler? What is the language? All those things. This is a very common term that we usually talk about. What is a compiler? So what the compiler says, it is a program that reads a program written in one language and translates it into another language. Now, if you find a sentence, this contains some keywords like language. First is the language. When I talk about the language, definitely this is a computer related language. And this language is not like our Hindi or English or any other language, but this language is actually a programming language. You must have heard the name of the programming languages: C, C++, Fortran, Pascal, Basic. So there are many languages are there. So any program that you have written in a language, it means to say that. And when you say a program, meaning program is a set of instructions that has been written for a specific objective or a specific problem solving. That is what is a program. And program has many characteristics. You might have studied that. If you have studied the programming language paper, then this paper says what exactly is a program, the characteristics of a program. But here we take this program as a keyword, and this program written in one language, and then it is being translated to another language. So what is that language it has been written? What is the language that has been the another language? So those things we'll study in this compiler design. So the block says, the diagram says, if there is a input as the source language, then the output is the target language. So what is our source language? What is our target language? Source language is the language in which usually we write the program. May it be a C, C++, Java, any language when we write, that is a source language. But the language in which we write the program is not understood by the computer, right? Because computer is a machine and it cannot understand in which language we write the code. So it has its own language. When it has its own language, this language will say, this language will be generated or this will be created by a special module or by a special software or a special system, you can say. And that is what is the compiler design. Traditionally, compilers go from high-level language to low-level language. As I said, the program that we write is a user-friendly or user-understandable language program. So that is what is called the high-level language. Whereas the language to which the computer can understand is a low-level language, or what we say, the machine language. So this is the difference between a source language and a target language. And the software that allows this source language to the target language is the compiler design. Now in the compiler design, before entering for the details, we should get acquainted with few of the terminologies. One of the terminology is the compiler. It is a program that translates an executable program in one language into an executable program in another language. So when you write a C program, what you do? You first learn the syntax of C. You first understand the grammar of C, and then you start writing a program, right?
Madam,
Yes, ma'am.
Raj Roshan Pandey has raised his hand.
Okay.
Raj, you may ask whatever you want to ask. Unmute yourself and ask.
Yeah. Yeah, Raj, you can ask me the question.
Raj, you can unmute yourself and ask.
लेट हो गया था मैम, इसी के लिए कर दिया.
Okay. Otherwise, I'll do one thing, ma'am. Let them raise the question. I mean, let them do the hand raising and the questions they can chat. So that after a certain interval, I'll take a question answer session and I can discuss.
Okay. Sure.
I think that will be better. Okay.
Better. Okay, ma'am. Okay.
So a program that translates. Yeah. So when you write the C program, you understand the syntax. You learn its syntax, then you write the program. Meaning you follow all the protocols, all the rules of writing a program, because you understand that whatever you are writing should be an executable program, right? But again, that executable program is really not executable by the computer. So what it does, it converts into another executable program. And that executable program is only understood by the computer, not by the user. So both are the executable programs, but they are written or they are understood by the different entities in a different way. So what we expect the program produced by the compiler to be better in some way than the original. Meaning, whatever will be produced or whatever will be generated by the computer or the compiler should be easily understood by the computer, and the computer should be able to process it. Now, there is another similar term as compiler is called interpreter. The meaning is same. Literally, if you go, the meaning is same as the compiler. But there is a difference in compiler and interpreter. The difference is that, Suresh Kumar, can you please mute yourself? So the next one is the interpreter. It is a program that reads an executable program and produces the results of running that program. What it says, it has the same job or it has the same responsibility as a compiler, but there is a slight difference in this. If you have worked in BASIC or if you have worked in Pascal in any time, then you will understand that Pascal or BASIC, they are the interpreters. We don't say them as the compilers. The reason behind is what the interpreter does, it translates one statement, it executes that statement, then it goes to the next statement. Before it goes to the next statement for interpretation, it first executes, then it goes to the next one. But in a compiler, what happens? It translates the whole of the statements, whole of the program at a time, then it takes the whole of the program for execution. That is the only difference lies between a compiler and an interpreter. Other than that, both remains the same. So in our course, we'll be mostly studying about the compilers, but some of the features or most of the features you can say of the interpreter is also same as that of the compiler. So here comes an abstract view of our compiler. What is a compiler? As I said, the input to the compiler is the source code. The output to the compiler is the machine code. And there is another outcome of the compiler, which is called the error. And this error is nothing but it goes to the user who generates the source code. So when the user generates the source code and it is fed to the compiler checks for different kind of errors. We will see what are the kind of errors later, and those errors are being reported to the user for modification. And this process, what you say, is the debugging. If you are writing the codes, you must be well aware of this. What do we mean by debugging is you are fixing the errors of your program. There could be many types of errors. We'll see to them one by one, the different kind of errors. There could be a syntax error, there could be a semantic error, there could be a logical error. So there will be different kind of errors will be there. And the compiler identifies each of these errors and inform back to the user so that the user modifies accordingly. So the compiler recognizes the legal programs. Legal programs means the programs written as per the protocol of a language. Then it generates the correct code. The correct code is the correct machine code. To manage the storage of all variables and the code. So whatever variables you are writing in a program are being stored in the compiler, and they are processed or they are accessed accordingly. Finally, it is an agreement on format for object or assembly code. So what is an object code or what is an assembly code? Object code is nothing but the low level language or the code that the machine can understand. This is what is your object code. So this is how we talk about the compiler. So when we talk about the compilers, if you classify the compilers, basically they are called the single pass compiler, multi-pass compiler, load and go compiler, debugging, optimizing. These are the different kind of compilers or the classification of the compilers. Depending on how they have been constructed or on what function they are supposed to perform. So depending on their functionality, they can be classified as either of these two types of compilers. But the basic tasks that any compiler must perform are essentially the same. That is why they all bring together under one category called the compiler. So we will see few of this kind of compilers. Maybe mostly we'll study about the single pass and two pass compilers, how the things are being done in this kind of compilers. Now the next is the analysis and synthesis model of compilation. So the job that is being done by the compiler is the compilation. There are two parts to the compilation, or what you say, the whole of the compilation process is divided into two parts. One is the analysis part, another is the synthesis part. In the analysis part, what happens? The compiler breaks the source program into constituent pieces. If I highlight this, what it does, it completely scans the code and it breaks into small constituting pieces and create an intermediate representation. It is like when I say something, you first what you do, you may sometimes translate whatever I am saying to your native language to understand what exactly is happening, and then you process that translated language so that you can do the job. So what is my language may be sometimes difficult for you. So what you do, you try to understand or you interpret this into your language, native language, then you process it. And that is what is called the intermediate language or intermediate representation. So in this, the source program in the analysis method, it totally analyzes the program or analyze the code and breaks into small constituent pieces and create an intermediate presentation of the same. Then after this analysis is over, it goes to the synthesis part. In the synthesis, it constructs the target program from the intermediate representation. Meaning, as I said, my language is converted to your native language. So that becomes an intermediate presentation. Now you work upon that intermediate presentation and work on that or construct the target program or process whatever you want to do that. That is what is your synthesis. So your analysis and synthesis are the two major things of your compilation. Here you can see in this figure of the compiler design, your source language enters to the compiler and the outcome is the target language. So in between there is an intermediate language. And this intermediate language has got two components. One is the front end, which is language specific, meaning which is language specific to the user. This is more close to the user side. And the other part of the intermediate language is the back-end machine specific. And so the front end is language specific, in which language the code is written, and the back end is the machine specific, for which machine it has been interpreted. So one is at the high level side, another is at the low level side. This is how your synthesis and the analysis of the program or of the compiler takes place. So now you can see the detailed picture of the compilation steps or what are the phases. As usual, the initial entry is the source language, the final outcome is the target language. In between, you have the intermediate languages. Now you will see there are two intermediate languages. One is at the user side, at the front end, another is at the machine side. What you say is the back end. So in the front end of the intermediate language or at the user side of the intermediate language, there are three steps or three phases. One is the scanner or what is called the lexical analysis. Another is the parser, which is a syntax analysis. Another is the semantic analysis, which actually generates the intermediate code. Right? So you will see and at the back end or at the machine side of intermediate language, there are two components. One is the code optimizer, another is the code generator. So in the intermediate language side of the, or you can say the front end side, the outcome of the lexical analysis or outcome of the scanner is nothing but the tokens. So there are some tokens identified in the code or in the program, and those tokens enter into the parser. So what the parser does, it does for the syntax analysis. And the outcome of this parser is your syntactic structure. We'll see each of these steps one by one. And this parsing or the outcome of the syntax analysis enter into the semantic analysis. The semantic analysis does the intermediate code generation, and that code goes for optimization to the backend, the backend intermediate language. And once the code is optimized, the final code is generated for the machine. And this is actually is in the machine language or actually the object code. And you'll see that all these stages or all these phases are connected to a very important entity called the symbol table. The symbol table is connected to each of the phases, and how it functions with these phases we will study subsequently. So what are the compilation steps or the phases? As we studied in the diagram, the first one is your lexical analysis phase. This generates the tokens in the source program. As we saw, the tokens are generated here. So this is what is the token generating phase. The next phase is syntax analysis phase. It recognizes the sentences in the program using the syntax of the language. If you are writing a C program, if you write C is equal to A plus B, it understands that you want to add two variables. This is a complete sentence, right? C is equal to A plus B. And you put a semicolon. So this becomes a complete statement, and this complete statement is understood by the syntax analyzer, meaning it understands that you want to add two variables A and B, and the addition of A and B will be stored in the variable C. This is what is the understanding after the syntax analysis. Then comes to the next phase, the semantic analysis. It infers the information about the program using the semantics of the language. Every language has got its own semantic, or own protocol, you can say. And this semantic is understood by the semantic analyzer, and it uses or it infers the information accordingly. So once this semantic analysis is being done, as I said, your intermediate code is being generated. So this intermediate code generation phase, what it does, it generates the abstract code based on the syntactic structure of the program and the semantic information from the phase 2. So what it does, it generates a code which is actually, you can say, the pseudo code, or you can say the abstract code, depending on the structure of the program, whatever has been written, whether you have an input statement at the beginning, scanf statement at the beginning, then you have a computation, then you have a printf statement. So what is the flow of your statements or flow of your instructions are being analyzed during this intermediate code generation phase. Once the code is generated, it needs to be optimized. So this refines the generated code using a series of optimizing transformations. When you will see that how these codes are optimized by using different optimization algorithms or optimization methods. And finally, you have the final code generation phase, and this final code is not for the user, but this final code is for the machine or for the system where the microprocessor, you can say, where the code will be executed. So what this does, this translates the abstract intermediate code into specific machine related code or machine instructions. So that way your source code passes through different phases of lexical analyzing, then syntax analyzing, then the semantic analyzing, then the intermediate code generation, then you have the code optimization, and finally you have the code generation phase or the final phase of your machine code or the machine instructions are generated. So before going to this, I can take a few questions. If you want to any question, I can take that. You can ask me any question if you want to have any question. Okay, Suchitra, am I still not audible to you?
No, ma'am,
Yeah, you
you
can
are
continue.
audible. You are properly audible.
Okay, probably she is having some problems. So she has mentioned that please speak slightly loud, but I think I am already giving my best effort. So if I go more loudly, uh, maybe we cannot stretch up to that much time. But I think this should be audible for everyone. So you can look at your, I mean, your mic side or the speaker side might be some issues at your side. You can just check that. Anybody else? Any question if you want to ask, or I can just continue with my lecture. Okay. So to continue with this lecture, what we'll do is next stage is the basic thing. What we'll study is the lexical analysis, the first stage of your compiler design or compilers, you can say. This phase convert the stream of characters representing input program into a sequence of tokens. So there is a term called token. This term is used. Why I'm using this word here? It will be clarified sooner. What it does during the lexical analysis, your program or the code that you have written is scanned character wise, character by character, every character. Even your space is also scanned. So when it is being scanned, it is converted into, or it is identified with different terms or different tokens representing a particular word or representing a particular meaningful information, you can say. That's what is a token. So this analysis convert the stream of characters representing the input program into a sequence of tokens. So here it says the tokens are the words of the programming language. So if I say scanf, it is a word of the C programming language and that will be considered as a token. If I say equal to, this is also considered as a word in C, so that will be also considered as a token. If I put a semicolon, that becomes also a token. So every word having a space in both the sides and having a meaningful information is termed as a token. So there is a term also called lexeme. This is nothing but the characters comprising a token. The tokens are also called the lexemes. For instance, the sequence of characters static int. This is a very common term that you are using in C programming, right? So one is the word is static, another word is the int. So this can be recognized as two tokens. As I said, a specific word having a meaningful information is called a token. So static becomes one token, int becomes another token. So this represent two words, static and integer, or sorry, int. These are the two tokens in your programming language. Similarly, the sequence of characters x plus plus, meaning x is incremented. So if that is the thing, the sequence of characters x plus plus is recognized as three tokens. The reason behind is, sorry, before x there is a star also. Star x plus plus is recognized as three tokens. So what are the tokens here? One is the star because it has a meaningful information, right? It signifies either it signifies a pointer, sometimes it signifies a multiplication operator. So that has a significance. So this can be called as a token. Another is the x. This of course is a variable, so it has a meaningful information, and this is also a token. And finally is the plus plus, the incrementing signal, a symbol. Incrementing says that the value will be incremented by 1, or if you want to increment by multiple values, so that has to be mentioned. This is what is the 3 tokens in this statement. Then the lexical analysis removes the white spaces, meaning all the spaces between before the token and after the token. So after removing the white spaces, whatever is the word that is remained and that signifies a meaning are considered as tokens, and they are being filtered from the program through this lexical analysis phase. And it removes the comments. You know that every program, whenever you write a program, you write the comments into it. Why you write the comment? So that the documentation becomes easier. The understanding of the code becomes easier. But that understanding is for you, not for the computer, right? So when you write the comment, it has nothing to do with the computer. The computer never takes your comments, never reads your comments, never executes your comments. So what it does, when you write a program with a comment, when it goes to the lexical analyzer, it simply omits all those comments because you put a symbol at the beginning of the comment. So once this symbol is scanned by the lexical analyzer, it understands that this is a comment and this is a non-executable statement. So as soon as it becomes a non-executable statement, the lexical analyzer removes it from the code. And whatever is left, only the tokens that are being scanned or that has been filtered from the lexical analysis, it goes to the next stage. And what is the next stage? We'll see. But before that, we'll see something more about the lexical analysis because we can understand in better way what exactly is the lexical analysis is. The first phase of a compiler is called the lexical analysis or scanning. We have understood that. Scanning means it scans word by word, it scans character by character. So this is what is the lexical analysis. The lexical analyzer reads the stream of characters making of the source program and groups the characters into meaningful sequences called lexemes. And these lexemes are same as also your tokens, right? So for each lexeme, the lexical analyzer produces as output a token of the form as token name and the attribute value. So a lexeme, whenever it is being generated or whenever it is taken, this is taken as a lexeme with two values, the token name and the attribute value. And that is what is also is called a token. This passes the next phase syntax analysis. This token name or the attribute value or the lexeme that is being generated or that is being filtered out in the lexical analysis are sent to the second phase or the syntax analysis phase. In the token, the first component is the token name. This is an abstract symbol that is used during the syntax analysis. So this token name is used by the syntax analyzer as an abstract symbol. And the second component of the lexeme, the attribute value, this points to an entry in the symbol table for this token. We'll see that what exactly is the attribute value is and how it is being used by the symbol table. So information from the symbol table entry is needed for semantic analysis and code generation. This symbol table is mostly used by the semantic analysis, not for the syntax analysis phase, or not for the lexical analysis. But these attribute values are stored in the symbol table and they are used for the subsequent stages of semantic analysis and code generation phase. We'll take an example of a lexical analysis. Now you see, let us say there is an input statement, result is equal to A plus B star 10, right? Now this will be entered into your lexical analyzer. So what the lexical analysis does? It scans every character by character and first finds that identifies the tokens. So what are the tokens here? The first token is the result. It is a string of characters with removed blank spaces before and after. So this becomes a token. Next one, equal to. It has a meaningful notation. So this becomes another token. A being a variable is become a token. Plus having a meaningful interpretation becomes a token. B being a variable becomes a token. Star being an operator becomes a token. 10 being a meaningful number becomes a token. So now we find that in this statement, result is equal to A plus B star 10 has got 1, 2, 3, 4, 5, 6, 7 tokens. And out of all these tokens, there are few can be the identifiers or what I say is the variables, and few tokens can be the operators. So in this, you will see the result A and B are the identifiers or they are the variables, whereas your operators are equal to, plus and star. And 10 is a constant identifier, so this can also be considered as a constant value. Neither it is a variable nor it is an operator. So this is how your lexical analyzer analyzes each of the code or each of the statement in the programming language. To see more example on this, let us say there is a statement called position is equal to initial plus rate into 60. What does it mean? This is a statement, right? This is it's a programming language. You have written so many programming languages, so you can easily understand what it means to say. So now when this statement enters into the lexical analyzer, the characters in this assignment could be grouped into the following lexemes. We'll see what are the different kind of lexemes here, and mapped into the following tokens passed on to the syntax analyzer. Before it enters into the syntax analyzer, they are found or they are generated as the tokens. So the first word or the first identifier is position. This is the lexeme, or this is, you can say, as a token as well. This is a lexeme that would be mapped into a token with identifier and the attribute, where ID is an abstract symbol standing for identifier. As I said, token is nothing but this position is an identifier. So what is the token if I say? Now position is a token identifier. So the kind of the token is, it is an identifier. It is a variable. That's what is your token says, or the attribute says. Sorry, the token name says. And the attribute is 1. Here 1 points to the symbol table entry for the position. That means in the symbol table, at the entry with address 1, the position has been stored, or this token has been stored. So the symbol table entry for an identifier holds the information about the identifier, such as its name and type. Type could be integer or real or whatever may be, that has to be stored. So that means here in the statement, when you write, the lexeme position will be identified through this lexical analysis as a token name and the attribute of the token 1. Now 1 means if 1 is reserved for an integer type or 1 is reserved for a floating point type, then the position, the identifier position will be treated accordingly. Whether it will be treated as an integer type or it will be treated as a floating point type. Then comes the equal to symbol, or what we say is the assignment symbol. This equal to is nothing but your assignment symbol, right? So now the assignment symbol equal to is a lexeme. This is also an lexeme, right? Or this is also a token. That is mapped into the token equal to. Since this token needs no attribute value, we have omitted the second component, meaning it doesn't have any attribute. It doesn't need any attribute type. So only the name is the equal to. So this lexeme contains only the token, which is an equal to symbol. Then another is the identifier is the initial. Initial is a lexeme that is mapped into the token ID and the symbol table number is 2. So here is also it is an identifier. So what is the identifier? That is it is a type of the token is an identifier. Sorry. And 2 is the symbol table entry where it goes. The next token or the next lexeme is plus. So plus is a lexeme that is mapped into the token plus. It also doesn't need any identifier type. So it is simply mentioned as the plus symbol. No attribute type is defined for this. Then another identifier or the lexeme is the rate. This is also mapped into the token ID and 3 where 3 points to the symbol table entry for the rate. So that means it goes to the third location of the symbol table where it has been stored. Again, the star is a lexeme. Star is a lexeme that is mapped into the token with no attribute value. Only the name of the lexeme or name of the token is enough. 60 is another lexeme. 60 is a constant number, right? It is not an identifier. It is not a variable, but it is a constant. So this is also a lexeme that is mapped into the token with the value 60. So this is how one statement of your coding of your programming language is being lexically analyzed to identify the tokens or to identify the lexemes. And these lexemes having two components, the name of the token and the attribute of the token. So this is how it is being scanned or it has been separated from the coding language. Here it says blanks separating the lexemes would be discarded by the lexical analyzer. As I said, the blanks will be deleted because they have no significance, but of course it has to be there to separate the tokens, to separate the lexemes in the code. So here comes a picture, a diagram of this translation of an example assignment statement. The same statement is being assigned here. If you will see the picture, it says the position is equal to initial plus rate into 60. This goes to the lexical analyzer. What the lexical analyzer does, it first puts a first lexeme. What is the first lexeme? It says the identifier, and the identifier is nothing but your position and its symbol table entry. Symbol table entry is position. Here is you have the symbol table if you can see. The first entry is the position, and all the details about this will be stored here. Now for the timing, we have put it the dotted lines. So this is stored in this position. Then it goes to the next one as equal to. Equal to is only the name of the lexeme or name of the token. It doesn't have any attribute type. Then we have the next one. Initial is identified or the third lexeme with the identifier and the symbol table entry is 2. Then you have the operator plus. Then you have the next lexeme ID, which is nothing but your rate, and the symbol table entry is 3. With the next lexeme only equal to symbol followed by the constant lexeme which is equal to 60. So your position equal to initial plus rate into 60. This is your statement that you wrote for the program. But when it passed through the lexical analysis, this is identified or this is converted into this format. Now it goes to the syntax analyzer. We'll see what happens in the syntax analyzer. The latter part, for the timing, because we are studying about the lexical analysis, we understood that this has become, or this has been changed to the lexical analysis in this form. So I'm skipping rest of the things for the time being before we go for the next thing. Then comes your syntax analysis. This syntax analysis is the second phase of your compiler as we studied. First is lexical analysis, then comes your syntax analysis. And this syntax analysis is also called as the parsing. Sorry. Just 1 minute. Yeah. So the next stage is your syntax analysis. This syntax analysis is the second phase of the compiler, and this is also called parsing. Here you have a component called the parser or the syntax analyzer. The parser uses the first components of the tokens produced by the lexical analyzer to create a tree-like intermediate representation. Meaning, the first component of the token means the ID, the lexemes with its first components. Those are being used by the parser to create a tree-like representation that depicts the grammatical structure of the token string. So the parser uses the first components of the tokens produced by the lexical analyzer to create a tree-like intermediate representation. If we'll go to the previous diagram, you will see the outcome of the syntax analyzer here after the second stage, or this is also a parser. This has got a tree-like structure. What is that? The first component or the first lexeme is here at the left branch of the tree. Then at the root, you have this equal to symbol or the assignment symbol. Then you have the next lexeme goes to the left child of the subtree. Then the plus becomes the new root of the subtree. Then star becomes the new root of the subtree. Then the third lexeme, this lexeme go to the left child of the tree subtree, and 60 goes to the right child of the subtree. So that means whatever we understood here, the outcome of the lexical analyzer goes as the left and right child of the tree, and they form a total tree-like structure by the parser or the syntax analyzer. A typical representation is a syntax tree in which each interior node represents an operation and the children of the node represents the arguments of the operation. This is what is the understood or what is generated by the syntax analyzer or the parser. Now coming to this, your picture, you will see that the tree has an interior node labeled star with ID 3 as its left child and the integer 60 as its right child. If you will see this, here is the one. Here is the interior node and it is ID 3 as the left child and 60 as the right child. The node ID 3 represents the identifier rate. The node label makes it explicit that we must first multiply the value of rate by 60. If you have studied data structure, trees in the data structure, you will see that this is nothing but your infix notation of your equation. Meaning, in this kind of structure, what will be the order of computation? If you can tell me, I'll be happy. What it does, first the lowermost children will be executed or they will be operated by the operator star. So ID3 and 60 will be multiplied first. Whatever will be stored, that will be stored here. Then that result and ID2 will be added with the summation symbol and the result will be stored here. Then that value will be assigned to the ID1 because there is an equal to symbol here. That means what it says, it follows the rule of your mathematical operation or the precedence. You know the Gauss rule, right? Bracket of division, multiplication, addition, and subtraction. It follows the principle of arithmetic operation. So accordingly, the tree is being generated, and during its infix traversal, you can say the operation is being carried out accordingly. The node level plus indicates that we must add the result of this multiplication to the value of initial, and the root of the tree labeled with equal to indicates that we must store the result of this addition into the location for the identifier position, as I described. So this syntax analysis also follows the arithmetical rule of Bodomas. Accordingly, it does the operation in the syntax analysis stage. So now what is this parsing or what is this syntax analysis? It uncovers the structure of a sentence in the program from a stream of tokens. For instance, the phrase x is equal to plus y, which is recognized as 4 tokens, as we have seen. What are the 4 tokens? X equal to plus and y. And this has the structure like equal to x plus y, bracketed y. Or you can say this has been in the prefix notation. If you have studied about the prefix, infix, and postfix notation of an equation, you will see that this equation is in the prefix notation, and accordingly, once it is converted to prefix notation, it becomes easier to execute. So whenever, because the computer always understands the prefix notation, so any equation that is written in the code or in the program, by the parsing, it is converted to the prefix notation so that it can be easily computed by the computer. That is an assignment expression that operates on x and the expression is plus y. So build a tree called a parse tree that reflects the structure of the input sentence. This is what is the job of your parsing or job of the syntax analyzer. It creates a tree. It builds a tree so that the input sentence is being fed accordingly or put accordingly in the structure like a tree. So here the grammars are how it is being generated. The grammars, you have the expression. This is your assignment symbol. You have another expression. You have an operator. You have another expression. So here also it says one expression, then another operator, then expression. So these two expressions are operated over this operator, and that is stored as an ID. And that stored number, that ID is also denoted as a number. So we say that assign this ID is equal to the expression that is being generated. This is what is your, that is what is your syntax analysis or the grammar of your data. Here comes. As I said, Here is a clear-cut picture how the tree is being generated or how the tree is being passed by the syntax analyzer. Result is equal to A plus B star 10. If you convert this to prefix notation, what will happen? This is an infix, right? You know what is an infix and what is a prefix. So this is in the infix notation, and this infix notation can be converted to a prefix notation. By this, what will be the outcome will be initially there will be the equal to symbol, and that equal to symbol is nothing but your assigned. Then after that your result comes. So result goes to the left tree. Then when it comes to the right tree, it comes to in the prefix notation, the operator comes first. So A plus B will be written as plus AB. So here it is plus, and A goes to the left tree, and to the right tree when it is supposed to be B, but B has again been operated with 10. So in the prefix notation, your star goes to the root of this or the right child of this operation. Then its left operator or left child will be the B, and the right child will be the 10. So now this is in completely infix notation. So once this will be studied, the computer understands, it will do accordingly or it will execute accordingly. This is what is the outcome of your syntax table or syntax analysis. It generates a tree-like structure. So by now we studied the lexical analysis, which identifies the tokens. Then these tokens enter into the syntax analysis where the tree is being generated. Now it comes to the semantic analysis. When it comes to the semantic analysis, this is concerned with the semantic of the program, meaning the meaning of the program, the reason of the program, what the program wants to do. So the semantic analyzer uses the syntax tree and the information in the symbol table to check the source program for semantic consistency with the language definition. This also gathers the type information and saves it in either the syntax tree or the symbol table for subsequent use during the intermediate code generation. As we know, the code has to be generated in the intermediate stages. So this semantic analysis does the job of intermediate code generation. An important part of the semantic analysis is type checking, where the compiler checks that each operator has matching operand. Sometimes you must be getting an error, like if you declare A to be an integer, but you give A as a floating point value, you get an error, right? Why that error has come? Because you announce or you declare A to be an integer, but you are assigning something, a floating point value to that. That becomes an error. So those things, type checking and those things are being checked by the semantic analysis. For example, many programming language definitions require an array index to be an integer. Of course, all of us do that, right? Array, when we say the index is always from 1 to n, where 1 to n being the integers. And suppose you say that no, the array index will be a real number or a floating point number, you are going to get an error, definitely. And who does that? Who checks that error? Is the semantic analysis. So the compiler must report an error if a floating point number is used to index an array. If I say A bracketed 1, this is accepted because it follows the grammar, it follows the rule of writing the index. If I say A bracketed 1.5, definitely this is an error because that is a logical error. That's a semantic error. It doesn't go with the information or it doesn't go with the purpose of writing the code. So definitely being the user, you get an error for that. That is what is the semantic analysis does. And after this semantic analysis is over, as we studied, the intermediate code will be generated. So what is this intermediate code generation? In the process of translating a source program into a target code, a compiler may construct one or more intermediate representations, which can have a variety of forms. Meaning, before the final compilation or before the final object code is generated, multiple stages of intermediate code will be generated. And each of this intermediate code will be evaluated, it will be processed for the next steps. So syntax trees are a form of intermediate representation. If we'll see the picture, the diagram that we saw, let's go back to that diagram. Yeah, here you see. Now the first is lexical analysis. We got all the lexemes. After that, the syntax analysis, we got all the parsing tree. And then after this, in the semantic analysis, we get the different type of matching or type things into this. So into to float, all those things, int to float, that is being generated because 60 was considered as an integer. Now, if you want to convert that to 60.0, that will be changed to integer to floating point. So that type matching is done in the semantic analysis. Then comes the intermediate code generator. Now you see what it does. It takes the first term T1 as integer to floating point 60, meaning 60 will be considered as 60.0 instead of only 60, because some of the operations will be requiring a floating point. So that has to be done as task 1. Then the task 2 will be ID3 into T1. This is what is T1, right? Task 1. So this task 1 will be multiplied with the ID3, this days. So this becomes your task 2. Then coming to the task 3, it will be ID2 in plus the task 2 or T2. So now T2 is here. This will be added with ID2. And finally, the ID1 will be equal to the task 3. Whatever is received here as task 3, that will be assigned to the ID1. This is what is the one of the intermediate code generator or one of the way of intermediate code generation. This is what it says. Syntax trees are a form of intermediate representation. They are commonly used during syntax and semantic analysis. So after the syntax and semantic analysis of the source program, many compilers generate an explicit low-level or machine-like intermediate representation. As I said, T1, T2, T3, task 1 to task n will be generated. That is one way of generating the intermediate representation. And this intermediate representation should have two important properties. What are they? It should be easy to produce and it should be easy to translate into the target machine. So as I said, T1, T2, T3, this nicely explained. Task 1 is such and such, task 2 is such and task 3 is this and this, and finally this is the task 4. So this is what is the one way of generating the intermediate code by the intermediate code generator phase. Then comes the code optimization. Once this intermediate code is generated, the code needs to be optimized. So what is that? The machine independent code optimization phase attempts to improve the intermediate code so that better target code will result. Now the intermediate code that is being generated is in a very raw stage or in a very preliminary stage. That may not be understood by the machine. So it has to be policed, it has to be regenerated, or it has to go through multiple iterations so that the machine can understand it or it can easily be understood. So apply a series of transformations to improve the time and space efficiency of the generated code. So what it does, multiple transformations will take place so that the time is improved and the space is also. What is this time and space efficiency will be? Why we need this time and space? Why these two terms are being used? If you understand, any processor, any computer has got two major resources. One is the time of computation, another is storage of the program, right? Any program you want to execute, you want that it should be executed faster because you cannot wait a long time to get the answer. That is what it says. It has to be time efficient. So what we do, sometimes you improve your RAM, upgrade your RAM. Sometimes you upgrade your processor. Sometimes you upgrade your motherboard. Why? Because you find that your system is getting slower. Means it takes more time to execute. So that is what any computation, if it takes more time, it is not an efficient computer. So this code optimizer does in such a work in such a way that the intermediate code, whatever has been generated, will be polished and it will take less computation time. Further, the space is another important thing because you know there is a cache memory in the processor or in the microcomputer or microcontroller, you can say. There is a main memory, there is a cache memory, there is a secondary memory. We don't consider about the secondary memory. What we consider is the cache memory and the primary memory. So what happens, this cache memory or the primary memory, they are very small in size. Reason behind, they are very expensive. We cannot afford a big size of cache memory or big size of main memory. So what happens, but every program that needs to be executed has to be stored in the main memory, primary memory, right? And your primary memory size is small. Now what is the solution you can do? You can reduce the size of your main program so that it occupies less space in the main memory or in the cache memory and gets executed. That is what it says. Apply a series of transformations to this intermediate code so that it becomes time efficient, meaning it does not take much time of computation, and it also consumes less space in the main memory, so that you can take the whole of the main memory or the code into the main memory and automatically the execution becomes faster. So there is something called a peephole optimization. This generates new instructions by combining or expanding on a small number of consecutive instructions. So there are several optimization techniques out there. We don't bother for this peephole optimization or something else, but it goes through multiple transformations so that your intermediate code generated becomes an efficient code. There is another optimization called the global optimization. It reorders, removes, or adds the instructions to change the structure of the generated code. These are the different transformations that takes place for the optimization of the code. This code optimization consumes a significant fraction of the compilation time. You'll see if your system takes some time for compilation, you understand that this is generating this is optimizing the code, because your token generation doesn't take much time, or the lexeme generation doesn't take much time. Your tree generation parsing doesn't take much time. Your semantic analysis doesn't take much time. So what takes time is the code optimization, because several algorithms has to be executed so to optimize the code that has been generated. The optimization capability varies widely. Of course, the systems having different capabilities will have the different optimizing time or optimization efficiency. This is what is called the code optimization. So your intermediate code that was generated after the semantic analysis enter into the code optimizer, and the outcome of the code optimizer is the optimized code, the polished code, the better formation of the code, but that is not the final code. So you have the next thing, final code, Before that, there is one slide for the code optimization. Again, just we can go through it. What it says, a simple intermediate code generation algorithm followed by code optimization is a reasonable way to generate good target code. This is what we understood. The intermediate code generation has to pass through a code optimizer. The optimizer can deduce that the conversion of 60 from integer to floating point can be done once and for all at compile time. So the int to float operation can be eliminated by replacing the integer 60 by a floating point number 60.0. What it says, in your code generation, you said that the 60 will be treated as a floating point. So you are using a symbol, or you are using a operator conversion from integer to float into float, so that every time this is executed, this will take the number 60, it will convert to 60.0 or to a floating point number, then again it will pass. It will take some time, right? So instead of that, the optimizer, what it does, it understands 60 has to be considered as a floating point number. So what it does, it simply writes 60.0. So for once and for all time, this will be considered as 60.0. No need to convert every time it will be used. This is what is the optimizer does. There is a great variation in the amount of code optimization that compilers perform. In those that do the most, the so-called optimizing compilers, a significant amount of time is spent on this phase. As we have studied, the code optimization takes some time for the optimizing the code. And this is the final stage of your compiler, the code generation stage. So the code generator takes as input an intermediate representation of the source program and maps it into the target language or the machine language, right? This is the final code generation. If the target language is machine code, registers or memory locations are selected for each of the variables used by the program.
नेटवर्क आहे ऑन कर दे क्लास हवे तर मैवा
So what we are doing, when the code is being generated, the registers or the memory locations are selected for each of the variables. As in our case, position was one variable, then rate was one variable. So for these variables, which memory locations has to be stored, that will be identified and they are reserved for that. Then the intermediate instructions are translated into the sequences of machine instructions that perform the same task. So map instructions in the intermediate code to specific machine instructions. And also the memory management, register allocation, instruction selection, instruction scheduling, these things are being done by the code generation. If you have studied the operating system, you know there are different schedulers are there, right? Resource allocation, memory allocation, CPU allocation, scheduling. So these are the different kind of techniques, or these are the different, resource allocation takes place by the computer. And this is the thing that takes place during the code generation phase. So for a compiler design, when the code is being generated, all this memory management thing, the register allocation thing, instruction selection thing, instruction scheduling thing, these things are being executed for the execution of the code. This generates the sufficient information to enable a symbolic debugging. This is what is called the code generation. So starting from, if you'll go for the diagram, you will see that. Now you see in this, we can easily understand the lexical analyzer. Output is the lexemes. It goes to the syntax analyzer. It generates the tree. It goes to semantic analysis. It converts into the appropriate form, meaning wherever required, it changes there. Then it goes to the intermediate code generator with a different task T1, T2, and T3 and all. That way it goes. Then it goes to the code optimizer. So what the code optimizer does, instead of 60 into float 60, it says that T1 is equal to ID3 into direct 60.0. So this task 1 and task 2 are changed into only one task, that is task 1. Can you see this? That means it has been optimized. So number of instructions are reduced. So what it says, T1 is equal to directly ID3 into 60.0. Instead of saying the converting this to floating point, it directly puts 60.0. So now ID1 becomes ID2 plus T1. See, here 4 statements were there, 4 instructions were there, or 4 tasks were there. Now these 4 tasks, after passing through the code optimizer, became only 2 tasks or 2 instructions. So that means it will now take less time to execute. It will now consume less space in the computer. This is what is the outcome of your code optimizer. Once the code optimizer is over, now it goes to the code generator. Here it does the machine language coding. What it says, R2 is the R1, R2 are the registers. As I said, it resolves the registers at the memory for the allocation or storage of data. So LDF is load the floating point ID3 to R2, then multiplication, then again load, then addition, then stop. So these 2 lines or 2 instructions after code optimizer is further given by the code generator into 5 statements. These are the machine language statements, or you can say microprocessor statements. If you have studied the microprocessor, you can understand what exactly they mean. So finally, from this position is equal to initial plus rate into 60 has now been converted to these lines. And these lines, 5 lines, will be entering into the computer for the processing or execution of the program. With this, I'll take some question. If you want to ask any question, you can ask me now. So any question from students? I can take a question, 1 or more questions if you want to ask me.
Students, if you have any questions, you can ask ma'am.
So if not, madam, I'll just give a break for 10 minutes to the students before we start the next.
Okay, ma'am. Okay, ma'am.
Is that okay? So that let them, get fresh up if they want to have some water.
Okay, ma'am. Students, you can also take a break for 10 minutes. After that, ma'am can start the session. Okay.
Yeah.
Okay.
I'll just start at 4:10, madam.
Okay, ma'am. Okay. Thank you.